Hello, everyone. My name is Parham Jalali from the Jalali-Lab at UCLA, and it's my pleasure to tell you about the time-stretch LiDAR, a fast 3D camera which has achieved record frame rate for a LiDAR. The co-authors are Kathy Jiang and Nino Krauth, two former members of my lab. Kathy is now with the company Waymo, and Nino is a faculty member at the University of Lübeck in Germany. This talk mostly follows a publication that came out in Nature Photonics in January of 2020. There was also a News and Views article about this work in the same issue. This LiDAR achieved record frame rate for a 3D camera. It was implemented using the discrete time version of the time stretch technique for fast data acquisition. The paper reported two different implementations of the idea, one using a fiber mode-lock laser, and the other using a frequency domain mode-lock laser, otherwise known as FDML. This is a spectrally scanned LiDAR, yet one that is also a time-of-flight system. By being able to do both in the same system, it achieved both high speed and high sensitivity. It has a fastest frame rate for any LiDAR, making it particularly suitable for high-speed 3D video in robotics and machine vision applications. Another unique attribute is that the illumination pattern is digitally controlled. So the LiDAR can adapt to its own target to avoid the superfluous data generation and to prevent the big data problem. Essentially, it performs foveated imaging, as we'll see later. LiDAR stands for light detection and ranging. It originated in the 1960s, shortly after the invention of the laser. It's a system for sensitive and accurate ranging. It has a number of applications. The one that has garnered the most attention these days is autonomous vehicle. At the same time, LiDAR has existing and very critical applications, for example, in mapping of wind patterns for optimization of wind farm for generation of clean energy, for creating 3D maps in geography, archaeology, forestry, in agriculture, atmospheric physics, and so on. LiDAR is a key component of the advanced driver assistance systems, ADAS, and also autonomous driving. Such LiDARs need to sense a fast-moving scene, so they need to be able to scan very fast and also have accurate range and good lateral resolution. For ranging, radar is a very mature technology, but radar has poor lateral resolution due to the large wavelength in the microwave regime. Cameras, on the other hand, have excellent resolution, but they have no intrinsic ranging capability. LiDAR offers the best of both worlds. It can measure the range like a radar, but also has good spatial resolution like a camera. The LiDAR we have developed is one of a growing portfolio of instruments based on the time stretch technique for fast real-time measurements of dynamic events. So let's take a short detour here to review the basic idea of time stretch. A typical time stretch system consists of 4 steps. The first step, modulates the data of interest onto the spectrum of a short optical pulse. The second step manipulates the time scale of the information using dispersive optics. The third step is detection, conversion to electronics, and A to D conversion, the critical step. And then once the data is in a digital domain, then it can be processed using GPUs, FPGAs, and so forth. The first 2 steps are in optical domain, and the second 2 steps are in electronic domain. This general framework has morphed into a powerful portfolio of instruments that perform real-time spectroscopy, imaging, with photometry and terahertz measurements at billions of frames per second, with non-stop recording spanning trillions of consecutive frames. So truly unprecedented performance that no other type of instrument can compete with. Another feature of these systems is that by virtue of their high real-time speed, they generate lots of data to the tune of terabytes per second of data being created. So they are a natural candidate for combination with deep learning, as we will see later. This idea was generated originally at UCLA in the 1990s. The first patent, filed in 1998, put forward two ideas. First, that wideband real-time data acquisition can be achieved via manipulation of the time scale in the analog domain. The second idea was how to implement such a system using a hybrid technique where the time stretching for data acquisition or time compression for data generation is done using optics with the rest of the system in electronics. In this way, the optical front end boosts the bandwidth and sampling rate of the electronic backend and overcomes the speed bottleneck of electronics. The time stretch instruments have been spectacularly successful. They have led to several discoveries of new ultrafast phenomena. One such phenomena is the optical rogue wave, which is spontaneous flashes of white light. These are statistically rare events that follow power law statistics, highly non-Gaussian distribution functions that are a hallmark of extreme events such as stock market crashes and natural disasters. They are statistically rare, and as a result, the detection of them using conventional pump and probe systems is not possible. The ability to observe such phenomena and perform tabletop experiments and then compare those results with models led to a new concept called the stimulated supercontinuum generation, which is a method for creating stable and broadband coherent light. Another example of a new observation enabled by time stretch was the first measurement of the birth of mode locking. Because mode locking is seeded by noise, its genesis is random, and until this report in 2016, no other instrument had been able to see how it starts. A time stretch system was able to capture the moment of creation of mode locking, showing that the complex exchange of energy takes place between when the laser undergoes a transition from CW operation to the mode lock state. This was a collaboration between UCLA and the University of Göttingen in Germany. Another example produced by the same collaboration is the use of time stretch technology for the first observation of the internal dynamics of soliton molecules. By being able to capture sequential single-shot spectra at very high frame rates, the study was able to demonstrate for the first time how the transition from an unbound state to a stable state happens, with orbits undergoing transition in discrete steps during the process. Yet another milestone is the work from the University of Lille in France, in which they use a time stretch digitizer to observe the real-time dynamics of relativistic electrons in an accelerator. A similar system has been deployed in the European Free Electron Laser Facility in Hamburg, Germany, for beam diagnostics. Back at UCLA in the late 2000s, we extended the time stretch technology to imaging and microscopy, leading to a new type of microscope. This system proved to be very useful for imaging of blood cells in high-speed flow through a microfluidic channel. This technique is called time stretch microscopy or time stretch flow through microscopy, and can capture images of cells with picosecond shutter speed to avoid motion blur. It can operate at up to 1 billion 1D frames per second for high throughput blood screening to identify few cancer cells that may exist among a large population of normal cells in early stage disease. Our focus has been to apply these instruments to biomedical imaging, and in particular to cytometry. By virtue of the ultra-high throughput, these microscopes generate about 1 terabit per second of data and are a natural candidate for neural networks and for data classification with neural networks. This combination of time-stretch microscopy and deep learning is very promising. The concept originated at UCLA in the late 2000s and has been refined there in the last decade. The latest is a technology called deep cytometry, which combines an interferometric time-stretch microscope for label-free imaging of cells at high speed with a low latency deep learning algorithm in the back end that can classify blood cells fast enough before they leave the flow channel so they can be sorted based on the phenotype. The time-stretch microscopy technology and its application to blood screening is being further developed in academic labs and startups in several countries by the alumni of our lab, including Keisuke Goda at the University of Tokyo. Since its introduction in the 1990s, the time-stretch technology has evolved into many directions, spanning scientific and biomedical domains. A comprehensive review appears in this Nature Photonics paper. After that overview of time-stretch, we now turn back to the LiDAR. The key requirement for any LiDAR are fast scanning to see dynamic scenes and high illumination energy per pixel for good SNR and to achieve long range. The current workhorse of scanning LiDAR is a mechanically scanned design that works pretty well. However, there are concerns about the reliability of mechanical steering, the cost, and also the large form factor. Current approaches to non-mechanical scanning include flash LiDAR, which uses a camera with flash illumination that is temporally modulated. Because the CW and flash nature of the illumination, the energy delivered per pixel is low, such that such a LiDAR does not scale well to long distance measurements. Another approach is electronic beamforming and beam scanning using an optical phase array. This could be a breakthrough technology, and great progress is being made by several startups in this area. At the same time, any phased array, whether it's optical or radio frequency, requires accurate control of phase, which is challenging for large arrays that have many elements. Our system described here represents a discrete time implementation of the time-stretch approach to imaging, but with the ability to also perform range measurements. The LiDAR starts with a broadband source, then a spectrotemporal modulator, described later, imparts a discrete chirp onto the original pulse. This converts the single broadband pulse into a sequence of pulses, each at a specific wavelength and unique time. A spatial disperser then maps this into space, converting the spatial information of the target into wavelengths. The scattered light is then captured by a high-speed and high-sensitivity photodiode. Although the spatial information is mapped into the wavelength, we do not need a spectrometer at the receiver to decode the image, because the wavelength is also mapped into time, The time of arrival tells us both the pixel location and the range. In other words, we can perform both imaging and ranging simultaneously. This is a timing diagram showing a sequence of pulses, space and wavelength and time, and what the return signal looks like. The key takeaway is that there's a trade-off between frame rate and the range. Higher frame rate reduces the range and vice versa. There is also a trade-off between the depth resolution being inversely proportional to the sampling rate of the backend digitizer. For such a spectrally scanned LiDAR to achieve a practical range, a good scan speed, and enough number of pixels, we need a chirp source that has microseconds duration and tens of nanometers of bandwidth. A tunable CW source cannot be used because the tuning speed is limited below a kilohertz. A dispersed supercontinuum source used in conventional time stretch systems cannot be used either because the maximum pulse duration that can be achieved by dispersion is only a few nanoseconds and is simply too short. To address this, we have developed two optical sources. The first shown here is a true time delay technique originally developed back in the 1990s in our lab for application to beam steering in phase array radar. It utilizes a pair of arrayed waveguide gratings, or AWGs, to apply a discrete chirp onto a broadband laser pulse. Such a source is able to achieve arbitrarily large discrete dispersion. It can stretch a supercontinuum pulse to microseconds or larger in discrete steps. The source achieves a time bandwidth product exceeding 10 to the 6. These are experimental point clouds captured using that source for the test target shown on the left. There are 30 spectrally scanned pixels on the horizontal direction, and the color represents the depth or the distance to the target. This LiDAR operates at 1 megahertz frame rate for 1D scan with 0.3 degrees of angular resolution. The second dimension is obtained through mechanical scanning, which can be achieved using fast galvo mirrors or acoustic reflector, as shown in later results. The second approach we developed for a chirped source with large time bandwidth product uses a frequency domain mode-locked laser, otherwise known as an FDML. The FDML generates continuous chirp with microseconds duration. The output from each cycle of the FDML was then subsequently modulated using an electro-optic modulator driven by a pulse pattern generator. Afterwards, the wavelength and time encoded pulse train is amplified to ensure enough energy is delivered to each pixel on the target. In other words, this is a master oscillator power amplifier or MOPA laser architecture. It achieves about 250 pixels in the lateral direction. Because the pulse pattern is digitally set through the pattern generator, the illumination pattern here can be digitally controlled and can be made to adapt to the target. So this LiDAR performs foveated imaging as shown next. These are experimentally measured point cloud of the same target as in the first approach, but here they're obtained using the second approach, the FDML laser followed by EO modulation, or the MOPA configuration. There are 256 spectrally scanned pixels in the horizontal direction, and the color again represents the distance to the target. Because the modulation pattern, the pixel pattern, is digitally generated, the LiDAR can perform foveated sampling. This means that the illumination pattern can be digitally adjusted, allowing the foveated sampling or foveated vision. This allows digitally controlled physical zoom, where the sample density can be digitally increased when needing a zoom. The left column here shows a uniform vision, where the pixel density is uniform across the target. The second column shows 2D zoomed with uniform vision, where the pixel density is digitally doubled in order to perform zooming. The third column, this is foveated imaging, where the central region is illuminated with higher pixel density than a peripheral vision. And the last column is also foveated imaging, but in this case, it's the opposite illumination pattern. The peripheral regions are illuminated with higher sample density than the central region. Using this foveated imaging technology, the data generated by the LiDAR could be managed to avoid generating superfluous data and creating a big data predicament for the backend. Now, the key attributes of our LiDAR are that it can illuminate a target with high energy pulses, and the illumination is scanned very fast in microseconds across the field of view. Well, these same attributes are also needed in multi-photon microscopy. So as a last part of this talk, I'd like to show you how the FDML approach, the second approach to the LiDAR, can also perform two-photon fluorescent microscopy and also fluorescent lifetime microscopy. Again, here the FDML laser output is temporally modulated using an electro-optic modulator. The output is then amplified to achieve enough pulse energy for two-photon excitation. The detection backend is similar to that in a LiDAR based on the time of arrival, the timestamp. We know which pixel the fluorescent emission came from. And by watching the decay of the returned signal, the fluorescent emission, we can also determine the fluorescent lifetime of the molecule. So this system has established speed milestones for fluorescent and the fluorescent lifetime imaging. These images show the two-photon fluorescent images on the left side and two-photon fluorescent lifetime images on the right side for the pollen grain on top and the Euglena algae on the bottom row. The images are captured at 300 kilohertz line scan, and the second dimension is scanned using a resonant galvo mirror. A fluorescent lifetime imaging, or FLIM as it's known, is a very powerful technique because it can identify different molecules that may have the same emission spectrum but different lifetimes. So it can distinguish molecules that cannot be distinguished using conventional fluorescent imaging. For example, the image of the pollen grain reveals that different lifetimes exist for the body and for the spike of the pollen, which is not visible in the fluorescent image. So in summary, we have reported and demonstrated the first spectrally scanned time-of-flight LiDAR that achieves a fast inertia-free scanning and imaging, and it can achieve adaptive or foveated vision. The LiDAR is obtained by two different sources that meet the requirement for a giant time bandwidth product for a chirped optical source. The same system has also achieved high-speed two-photon fluorescent and the two-photon fluorescent lifetime imaging with milestone speed results. It's been a pleasure to present this work to you. Thank you so much for your attention.